Hello, in this video we're going to take a look at all the gory details of the source code of the Arduino sketch that's running on the balloon, and there's also a sketch that runs on the ground to receive the signals from the NRF24, so we'll take a look at that as well. But what I'm showing you here is just a little bit of footage that I got after I received the parachute, and I just did a few drop tests to see how quickly it fell with a 100-gram weight. I just wanted to see that I wasn't wildly out of the range that I needed. So this footage didn't really fit in with any of the other videos in this series, so I thought I'd just put it at the beginning of this one.
Oh, that should be good. Alright, drop. That's not too bad. So, drop. Oh, look, it's swinging around and around a lot. Yeah, that's alright, that's not too fast and not too slow. Alright, let's see if my parachute dropping target accuracy is as good as last time. I want to get it about there. But I'll come over to the side a little bit more so we can see it. Instead of having it coming directly at us, maybe we can see it a little bit more from the side. Okay, ready? Go. Look at it spinning. It didn't do that the first time, did it? I don't recall it doing that. Oh well, about 15 meters off, not bad. This is how I've connected the weight there. It's just no knots or anything here, just a zip tie going to hold them together, and then the string going through there like that. So there's not really any twisting or anything. So I'm not really sure why it wants to spin around and round, but maybe this is a little bit short perhaps. If it was longer, maybe it wouldn't do that. Right, so there's very little wind now. Let's see what this one does. Go. No, it still spins around. About the same. Oh, yeah, about the same, I think. Okay, that'll do for today.
Here's another little bit of video that didn't really seem to fit in anywhere else. I'm just doing a quick check with the DVR and the FPV camera to see how much power they draw. It's about 2 watts consistently. They're going through a 5-volt regulator here. They're not taking that 7 volts directly. And I also checked what file sizes they create. So 5 minutes comes to about 220 meg. So you could get 20 minutes per gig, or about 6 gig for the 2-hour flight that I was thinking to do. So something like a 16 gigabyte card would be plenty. Okay then, I hope you have your strong coffee ready, because now we're going to take a deeper look at how all of this fits together, and we're probably going to be looking at a lot of source code for most of the rest of this video, I think. But just to start off with, I'll show you how all the connections are arranged, and then we'll have a quick look at the PCB as well to just see what that looks like and where everything fits onto it. So I've listed up all the devices or components here, and we can see what type of communication each one of those is using to talk to the Arduino. Well, Arduino doesn't need to talk to itself, so there's nothing here. GPS is using hardware UART. I've found in the past that often messages can be missed if you're not using hardware UART. Well, software UART is the other option, is what I mean. But software UART, yeah, I don't recommend that really for GPS, especially at faster refresh rates like 10 Hz and 5 Hz. I did not use fast refresh rates for this. I only went with 1 Hz because, as I mentioned in the previous video, a lot of this work has to be kind of slowed down and taken turns. All of these devices have to take turns, and so there wasn't any point having a faster refresh rate than 1 Hz anyway. Another thing that we'll need to keep in mind with the GPS is that ideally you don't want to have it in the default setting, which I think is pedestrian, so it's not expecting to feel large g-forces or large changes of direction and large velocities and things like that. But there are other modes called, I forget what the others are, but one of them at least is called airborne, and that is what is typically used for these sort of balloon projects where you are expecting large changes in vertical velocity and things like that. Anyway, the 2 temperature sensors, they are called DS18B20. I'm not sure if I mentioned that in my last video, and they have their own sort of a protocol that we'll look at. Well, basically you just get the library and you use the library and you don't have to think about it too much. The barometers, humidity sensor, accelerometer are all I2C. GSM cell module is working on software UART, because this one you can actually it doesn't need to be so fast, so it's fine to be using that one. Then the radio transceiver and the SD card reader, I managed to get these both working on hardware SPI. I actually tried this a couple of years ago to get these both working on hardware SPI together on the same bus. Of course, there's only one hardware SPI on this Arduino. And for some reason it just never really worked out, so I ended up tweaking the SD card SD card library to run the SD card on software SPI in that case. But I really didn't want to do that for this project because I was sort of running out of connections already, and SPI does take up quite a few wires if you want to do it with software, and it slows everything down, and I just would have really hated to do that. So I was very pleased to see that this time when I tried hardware SPI for both of them, it just worked. So maybe something changed in the SD card library, or this library perhaps, but for whatever reason I was able to use those both on the same bus, and that made things quite nice. Voltage regulator doesn't need any communication, so to sense the battery voltage I needed a voltage divider that just uses one analog in pin, and then the buzzer, which is just to sort of help you find it when you're walking around and you know you're close to it but you can't exactly see it or something. That was just the point of the buzzer, that's all it was for. That just takes one digital out, so it's one of those buzzers that's like I think they call them a continuous buzzer, and you just make the digital out high and it will just buzz at one pitch, so it doesn't have any, can't play any music or anything like that, it's just a simple buzzer. And the LED I ended up not using, I just sort of put that on there basically just to check that it worked, and I mean just for the sake of it, because I made my PCB to be able to do that, so I put it on there just in case I wanted it, but I ended up not using it. This is the website that I used to design my PCB. It's called EZEDA, and I think in my last video I called it JLC PCB, but that JLC PCB is actually the site, this one here, where you get the stuff manufactured and shipped out. But I think they might be operated by the same company, because there's a link in here to JLC PCB, so it makes it quite easy to just design and then upload to make it. So anyway, this EZEDA, I would say, has been one of the greatest discoveries for me in the last year or so when it comes to twiddling around with Arduino and electronics projects and stuff, because I think I tried 4 other software packages, either online tools like this, or there's a couple that are built into Linux. I mean, they're in the Fedora distribution packages that you can try, but all of them had some sort of a shortcoming I found. Either they weren't very intuitive to use, or I just couldn't achieve what I wanted to do. But with this one, within 4 hours of knowing that it existed, I was able to submit this first design here, and then it was built in 2 days, cost $2 or $7.65 including shipping, and I received it, I think it got to me in about 10 days or so. So I was really impressed. Anyway, let's have a little bit of a look at well, we won't look at this too much. You need to do something like this in order to get into the next screen, which is this one, where you actually lay it out. So this screen defines how the circuits needs to be connected. All the components need to be connected to each other. And as you can see, I've used every single, oh, not that one, but every single pin except for that one. That's just a raw power input where you can put up to 12 volts in. I haven't used that for anything, of course. But I've used all of the pins for something at some point. And when you've done with that, or you'll probably go backwards and forwards between this screen and this screen, where you actually lay things out. So, well, I'll just get you to, I'll share a link to this, and maybe you can just sort of click around, and I think you can clone it or something and modify it. But basically it's almost like using an image editing program here. You can turn the layers off and on, and when you click here you can just sort of drag the traces out to where you want them to be. Anyway, it's a great program, and you can also do this to see what it's going to look like as a 2D view, and you can also do this, which is pretty cool too. You can show it as a 3D view. Well, it doesn't twist that way too much, but oh yeah, we can twist it around like that. And this is really good because it just lets you see exactly what you're going to get. So I was, yeah, really happy to find this. And I think we might actually have to use this photo view to look at in the next little bit, because I found that when you're looking at the real life one of these, it's not quite so easy to see. So let's take a look over this. Starting from the top, we have the hardware UART for the GPS there, and that is using obviously those two pins there. This ground, by the way, it looks like it's not connected to anything. That's just because we're looking at the top layer. So if we look at the 3D view, and so that's that ground there. If we turn this board over, we'll see that this entire back face is the ground plane, and the ground is actually connected to that there. So all of the grounds are on the back, or connected through via the back. Over here we have SPI, and that's using the default pins for the hardware SPI bus. So Mossy and Miso are coming around to, what is it, 11 and 12. So 10, 11, 12, 13, they go straight through here for the SD card, which is also on the same bus. Over here we have an LED with a current limiting resistor, and then we have another one here, or you can use the buzzer. So obviously if you stick the buzzer on here, you can't have the LED as well, so you're either going to have two LEDs or one LED and the buzzer. What else have we got down here? So the software UART is running on pins 7 and 8 by the looks of it. The temperature sensors, they only need one pin. They're pretty neat, and they're running on pin 9. And turns out they need a 4K7 pull-up resistor, so that's what this is here for, not optional apparently. That was the only mistake I made in my first submission for the PCB. I was a little bit hasty. Yeah, so I can still actually use the first boards that I submitted. I'll just have to stick this resistor on some other way. Then we just have some breakouts here for these. I didn't use those. These ones here are for I2C, and you can see I've actually only used a couple there. So this is just the SCA and SDL, or one or the other. So that's them there, and they are labeled on the back. So the idea is that the SD card reader and your I2C devices, modules, will be stuck on the back like that. So you stack the I2Cs on top of each other like I showed you in the previous video. All of these pins are the same on quite a few of those breakout modules. And then this arrangement of pins here is the same as the SD card reader that I was using. That's about it really. So the battery will be connected on here, and there's a couple of resistors for a voltage divider there, and the center of that voltage divider is going into pin A1 by the looks of it. It was quite a while ago, a couple of months ago that I did this, but anyway, that's how that all looks. Here's a side-by-side look at my first design on the left that I made in 4 hours, a little bit hastily, and my second design, which I did when I took my time a little bit more. The only thing that's really important was, like I say, this 4K7 resistor needs to be there for the temperature sensors to work properly. But since I was doing a resubmission, I took my time and I added some smoothing cap possibilities like this one here and up there, which are not really necessary. Actually, this smoothing cap here, it really helps to have a little capacitor across the power terminals of the NRF24, well, which goes here, obviously. Yeah. And I also broke out all of the pins available like this, even though I'm not using them, and those ones there. And I also swapped the direction of these, or the ordering of these, to be a little bit more easier. This is the actual order that they are on the temperature sensor device itself there. And I also figured out how to make pads like this instead of a simple via like that, which wasn't really necessary. And I just tidied up the screen print a bit as well to make it a little bit more informative. Anyway, enough about that. Let's have a look at the source code itself. These are, or the bottom three here are things that I wrote, and the one at the top there obviously is libraries that you would add to your Arduino installation. There's not actually that many of them. The first two at the top there are both for the DS18B20 temperature sensor. RF24 is obviously for the radio transceiver, and then the SI7021 is the humidity sensor. And that's all that you'd need to add, because that's all the libraries that I use, because I had to change quite a few things, like I say, to make it sort of slow down and all the sensors have to take turns. There is actually one other library that I used, and that was the SD card library, but that was included in my Arduino installation, which is why I didn't list it up here. And the Arduino version I was using is 1.8.5, which occasionally does make a difference, so I just thought I'd mention that. So RFRX is just a very small sketch that is running. This is the one that you have on the ground plugged into your tablet to receive the information from the RF24 on the balloon. It's pretty simple. It just receives the packets and it turns them into JSON for delivery to the tablet. Sensor tests is a bunch of things that I made before I got started on the main sketch. This one here is actually, I think that might be part of the Arduino examples actually. It just sort of scans the I2C bus to see what devices are responding there. But what I wanted to do first was test each individual component to see how much program space and memory it needed to run, because I was a little bit concerned that with the, I think it's about 30 kilobytes or so program space and, what is it, 2 kilobytes of RAM? Yeah. That the Arduino Pro Mini has, I probably wouldn't be able to get everything that I wanted to work together. But after cutting everything down quite carefully and going over it with a fine-tooth comb to reduce all of the program space and memory that I possibly could, managed to get all of these to run together. But that's what these tests are here for, so that I could run them separately and see how much individually each one was and which one I would need to remove if it came to that. So with a balloon, this is the main sketch itself, and because there's so much going on in there, it's separated into different files just to keep everything a little bit more organized. So I think we will start by looking at that one. So this is the main file of the sketch that's running on the balloon. I'm just going to use Qt Creator to look at this because it has a lot better syntax highlighting, and you can quickly jump to other files and backwards and forwards like this, and you can list up the functions and so on. It's a lot better than the Arduino IDE just for navigating source code. Anyway, so there's actually not that much in this file, that's all of it there. And the reason for that is, of course, because we are including most of the stuff from those other files that we saw there. So each one of these components will have its own setup and loop functions like this. So you can see they're all doing their setups at the beginning. And there's a define for do serial here, which is off at the moment. If this is on, we will see some serial output given to the hardware UART. So that's like there, you can see that's what it would do if it was defined. And of course the weather balloon would not function like that because the GPS is supposed to be using the hardware UART, but this is just for some debugging purposes, can be handy. And we also need to, for a few of these things, the barometers in particular, we need to get their calibration numbers. So when these things are made in the factory, I guess they put them into a pressure chamber where they have a known pressure, and they read off the values that they're giving, and they adjust some calibration values inside the permanent memory of these to give the right readings. And because I was so strapped for memory and program space, what I had to do was get the calibration values off of these devices first, and do that as a post-process either on the tablet or on the receiving Arduino on the other end of the connection. Yeah, so that's one thing that the do serial will do. It will print out those calibration values for the barometers. Anyway, so that's the setups there, and we have our loops in an array of function pointers. So this is a function pointer. It's a bit of a weird thing, I had to look up how to do that actually, but these are just function pointers. So this GSM loop will be in the GSM file. Is that there? So GSM loop will be this function there. That's what that's going to do. And we have these things called phases, which I'll explain a little bit more in a second. So we have this array of tasks to do. You could consider these like a task. And this loop, the main loop of the whole sketch, is sort of doing a very primitive form of preemptive scheduling, I think you would call this, where we have a value called last task time, and we look at the amount of time that's passed since the last loop. And if it's more than 100 milliseconds, i.e. 1/10 of a second, we move on to the next task. So we increment first we call that function, whatever it was. So we'll be starting off with that one. So we'll call that function, and then we'll increment the task index. So now it's going to be pointing at the next one in the array, which is that one. So that next time, after another 100 milliseconds has passed, then we're going to call this one. So that just sort of makes it easy to put a large list of tasks to do and sort of schedule them and have them all running kind of at the same time, but not really. That's the point of this. And you'll see that it also lets you do something like this. You can put two of the same task in your array to just run them more often than others. So it lets you sort of share out how much CPU time they get. And this case, I think that's the buzzer is the only case that I use that for. And buzzer loop, if we just have a look at buzzer loop, can we do that? Oh yeah. So all that the buzzer does for its setup is say that that pin is a output pin, and then every time we call buzzer loop, it just changes this variable buzzer state to be 1 or 0, and then writes it to the digital pin. So what that's going to do is it's just going to turn the buzzer on here, and then it's going to turn it off there. So however long this VBAT loop function takes, that's going to be the length of our buzzer going beep, 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 like that. Hope that makes sense. So I found this very useful because another thing it lets you do is just take things out. So for a while I was having trouble trying to figure out what was causing things to be slow and so on. So you can just go like this and like that, and all of a sudden, just with that little change, all of this processing will not be done in the main loop. So it's quite handy to just sort of add and remove things from the list of tasks to do. So I mentioned phases just a minute ago, and let's have a look. Not all of these things need to have phases, but the purpose of phases is, let's look at the humidity sensor, for example. So the humidity sensor, the way you use this thing is you call humidity, measure humidity start, and then what do? Call measure humidity finish. Actually, maybe I should have looked at the docs a little bit before I did this. But basically, it's not a single step. It takes a little bit of time for it to actually do the measurement of the humidity to give you a value. And we don't want to wait. Basically, we don't want to sit around waiting for any individual one of these sensors to do something when other sensors could also be doing something. So we have just a integer value called phase. It starts off as 0, so the first thing we're going to do is that. And every time our loop function is called, we'll do whatever is the current task to be done for that phase, and then we will increment the phase number to be the next one. So let's figure out how often this would happen. This is going to run once every 4 times this loop, SI7021 loop is called. And if we go back to our weather balloon INO, the main one, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we've got 10 tasks, and we're running them in succession at about 100 milliseconds apart. In other words, about once per second. So the SI7021 that we were just looking at here, this is going to be run approximately once per second, and that means that each one of these phases is going to be run approximately once every 4 seconds. So that's why in some of the video that we'll see in the rest of the series, the numbers are not really updating that quickly. They're only updating every few seconds, so hopefully that makes sense. But we really did need to do that, especially for some of these. I think this humidity one was the worst culprit. It was really, really slow to do the measurement and actually give you a value back. And just to have another look at another example where we had to do phases, I think it was this one. So this is the temperature sensors, and they all do they have this sort of weighting thing as well, which takes a while. So here again we have a phase value that starts as 0, and same thing, we just increment it like that each time this loop comes through. And this has only 3 phases, so each one of these will be run approximately once every 3 seconds. So I hope that whole scheduling and organization thing makes sense. What else can we look at in here? Oh yeah, there are a few tasks that need to be done as fast as possible. These are mainly the UARTs. Input coming from the UARTs need to be read and cleared because there's a buffer for these UARTs. If we let it overflow, we're going to get nonsense and we'll miss messages. Especially for the GPS, we need to flush that buffer and read in any data that's waiting there as quick as we can. And GSM doesn't move so quickly, but we might as well check that that's been flushed properly as well. So these are put into a function called fast loop, and this fast loop function is called here. So it's outside of this once every 100 milliseconds thing. It's just going to run, basically it's like an idle loop. It's going to run as much as it can. And we also have in here RF24 loop, which is going to do the sending of the data packets to the ground, and that doesn't need to be super fast, but because it is a very fast function, basically you're just posting a little bit of data to the SPI bus and then that's it. The RF24 is what's actually doing the work here. And I thought since it's so fast, I might as well just call it as often as possible, because otherwise nothing is really going to be done. So this RF24 loop is what's taking up the majority of CPU time when none of these other tasks are being called. Let's also have a look at a few other points that might be worth noting. This is the GPS.h file, and if you've watched any of my other videos about UBX protocol, you've probably seen some of this stuff before. I'm using the nav PVT message, and a lot of this stuff I have just basically copied from some of my old sketches where I've done this stuff before. But just these last little bits here, some of this is a bit different. So I'm using 1 Hertz message rate for the how quickly the messages are sent from the GPS. And oh shit, I didn't comment this, did I? This nav5 one, this is where we say pedestrian set movement. It's like called movement mode or something. Mode to airborne. So this is what I was saying before about letting it know that it should be expecting some fast movements and high velocities and vertical changes and things like that, I think. Oh yeah, and another thing I came across which ended up being pretty much necessary is this config one, and what this will do is save the current configuration as the permanent configuration. So what that means in effect is if you do that once, you don't actually need to send all of this stuff to the GPS when it starts up, because it's just going to start up with what you told it to do last time. And this is very nice because it means that the Arduino can power up before the GPS powers up, and even if the GPS is not listening when the Arduino sends all of this configuration message, it doesn't matter because the GPS will remember what it was told to do from last time. So that turned out to be very handy. Now, speaking of problems caused by things powering up at different times, I also had to do a similar sort of a thing for the cell phone module to make sure that it would be in the right mode, that is internet HTTP mode, every time, and it was able to access the right network access point number or whatever they're called. Anyway, this is the GSM file now. There are 24 phases here. A lot of the phases actually do nothing, but they are there to make sure that the overall cycle is going to be 24 seconds long. So we have a bunch of stuff here that I've copied from some of my previous sketches again. Now the interesting thing about this sketch, oh, not that one. Interesting thing about this sketch is that the setup actually does not set up the cell phone module to be in the correct mode. So all it does is start the serial connection and say what phase we're in now. And if we look down here at the loop, we'll see we have, even though we have 24 phases, we only have a few cases for them. So this is just to make sure that they're spaced out in time so that each one has enough, well, mainly this one here, this HTTP action is the one that takes the longest time. So that's going to happen in phase 15, which is roughly about halfway through the 24 second cycle. So it's going to be about another 10 seconds before it comes back to do this one. And these two here are what you would normally put in your setup function because they only need to be done once. So this is where you set the access point network, Vodafone in my case. You cannot use Spark for this, I found. I tried to do this with Spark, doesn't work. You need the Vodafone, which is still running the 2G network. and we'll be running it until 2025 apparently, so that's another thing to keep in mind. You might not be able to do this after 2025 with this same equipment. Anyway, these two lines here, instead of going in the setup function to be called once at the beginning of the sketch, because it's taking 24 seconds and most of the time it's not really doing anything anyway, I thought I'll just put them in here, and it seems like it doesn't hurt to call them over and over. You might get an error actually, it might say error, but it doesn't, functionally it doesn't affect anything. And this does make sure that even if you lose cell phone signal, when you come back into range of a cell tower, everything's going to be working again because you're repeatedly telling it the right settings to use. So that's the first two phases. Those phases take a while. Oh, this one here takes a while. So I've left an 8-second gap before it tries to do something else. And the next thing it does is ask for the signal quality reading. So this is a measurement of how strong a signal it's getting from the closest cell tower that it's trying to talk to. And this is a number between 0 and I think 22 maybe, or 21 or something. And it's I don't think it's a linear scale, but it just sort of reflects a number of dBi signal, or dBm or whatever signal that it's receiving. So I just wanted to measure that as it was, as the balloon was rising up, to see how altitude affected the signal quality. The next one is CREG, which requests to find out whether we have registered on the network or not. So this will return a 0 if we have no cell phone connection. It will return a 1 if we have a connection, and I think it returns a 2 if it's currently attempting to make a connection. So basically anything other than 1 means that there's no connection. And I found that it was a little bit sort of redundant to have both signal quality and CREG, because if you don't have a signal quality, yeah, I never really saw it to be having a good signal quality and not registered to the network, put it that way. Anyway, so after all that, we have finally what we actually wanted to do, which was HTTP init. Again, I'm doing this every single time just to make sure that it's in the right mode. It doesn't seem to cause any problems. And then the parameters for the HTTP post, which are going to go to my server, are in this post data function, which are here. So that's the URL, and then we make a big get string like this and just post that to the web server. And as it says there, should leave about 9 seconds for the HTTP action to complete. Okay, here's the file that handles the logging to the SD card, and it's the same thing again. We have this phase that keeps incrementing, and at the beginning of this one we do have a little bit of a unique setup where we have to try and figure out a file name that's not in use yet. And you can see from this comment here that I came upon a few things that needed to be worked around like this. But anyway, the main loop of this one, all it does is in each phase it writes looks like 3 or 4 values per iteration of this loop. So we don't want to write these all at once, and because they're not updating very quickly anyway, there's no point. So we just write a little bit of them each time we're called, and then at the end of that we call flush, just to make sure that the file is actually flushed to disk, so if we lose power we don't lose the last set of things that we were writing. And then we increment the phase and just sort of repeat like that. And because we have 9 phases for this, it means that the SD card is going to receive 1 full logging entry every 9 seconds or so. And the last file that I wanted to look at from this sketch is the one that handles the RF24 module. So I've done this to death in a lot of my other videos, so I'll just show you what's different about this one. And that is the fact that I had to separate the data into 2 separate packets, because we have packet GPS, which is 29 bytes. The size of these packets can only be up to 32, and I wanted actually another 29, so what's that, 58 I think in total. And yeah, it just wasn't going to fit in one packet. So what I've done is I have 1 byte at the beginning of each of these packets to denote which type of packet it is, and the receiving end will need to know this, and that'll be one of these values here, PT GPS or PT sensors. So we have another one of those there at the beginning of that packet. And then in the first packet we have mostly GPS things, a little bit of sensor data there actually, and then this packet sensors packet has the rest of the sensors there. So apart from that, it's all just the same as any other NRF24 sketch that I've done in the past, I think. So that's probably far more than you wanted to know about all of that, but I'll just show you how much program space and memory that uses when we compile it, because I was quite pleased that I managed to get it down to this level. 24K program space and 1.5K of memory, which is 77-78% of those. And it looks like after 75% you get this low memory available, stability problems may occur warning showing up, but I think you actually have a fair bit of leeway after that, because I have not seen any problems that, weird stuff that would have been caused by lack of memory issues at this 77-78% level. Okay, now we're looking at the sketch called RFRX, which is the one that's running on the receiving end. How's your coffee? Holding out. We're almost there. So this, if we scroll down a little bit here, we'll see that we have two structures here, and they are kind of the same as what we saw before. We have sensors and GPS, and then I'm using a union of those because we don't know which one we're going to be receiving as the data comes in. It could be either of the GPS or the sensors packets. But once we've read the first byte in, we'll know which one it is, because both of them have this byte type at the beginning like that. Anyway, so we read in that data, and we don't pass it directly onto the Android tablet, because some of this data that we're getting, particularly the barometer data, as I mentioned earlier, it needs to have some calculations done to convert it from the raw value that the sensor gives to a value that means something to us, like altitude or pressure or something. Well, pressure for these two. So this needs those calibration numbers, which are here. So I got these from running one of those other test sketches that I showed you earlier, and those will just print out these values here so that you can copy and paste them in here. And I had two versions of this as I was progressing. I started just using a version on the breadboard, and then I built my PCB up, and you can see the values are a little bit different on each of these. So they are unique, and you'll need to get these numbers to get the correct values for pressure and so on. So there's a few functions here that do that conversion using those calibration numbers. Here's the calibration numbers for the MS5611. Again, breadboard build and PCB build need to be unique, separate numbers there. So all this does, if we look at the main loop here, we receive data from the radio, and then if more than 200 milliseconds has passed, we call this log JSON function. So every 5 times a second we're going to see this outputting some JSON onto the serial output. And here's the log JSON function there. So all it does is we should have an opening curly bracket somewhere. Oh, there it is. So we start this opening curly bracket just starts a JSON object, and then we just write all of those numbers out basically as one JSON object with these names as the properties, and then we close it. We should have a closing curly bracket somewhere as well. Where is that? There. So that becomes one output, and that's going to be every 200 milliseconds. Okay, I'm going to finish this video here. It's getting a bit long, and I think I've covered all the introductory stuff that I need to. The rest of this video series is just going to be put together from pieces of video that I've recorded over the last few weeks as I was testing this stuff, and so we'll see a little bit more of this guy here. This is my first prototype. I'm missing a few components that have been stolen for other things, but anyway, that will be in the next video, and since I only need to edit those together, they should come out a little bit quicker now. Thanks for watching. See you next time.